Okay, so this is the last problem for the property of materials for this chapter. So what we will look at is like there's a truss structure like this. Maybe you remember that design in statics in one of your homework. Anyway, that could be another one. But this is this truss, and on the bottom of the truss we have two pin connection, and we have some like friction pads. So they will help with the shearing force there. So we will look more specifically in this problem at this one to the left. Okay, and this is some information that we know. We found the forces inside. We know that the force on the lower left pin, this one, is 1.5 kilonewton. We also know that the angle there is 60 degrees. And we have also the dimension of the pads. Okay, so this pad, we know it's 100 by 75 by 25. And let me give you the dimension like this, 125. And in the other direction like this, like this, that will be 75, correct? 75, yes. This is the dimension that we have. And the question for you is, what is the shape at the end of this rubber friction pad? So we see that the force will push to the left and push down, so we imagine like the pad will look like this. Okay, but my question for you is like, what will be these new dimensions and what will be this little delta x? Okay, so let's work on that. So let's see, formula that we have. We need to find a new dimension h. So to find these dimensions, what we need is like, we know that the epsilon equal the delta y divided by the original 8. So we need to find the epsilon to find the delta y, right? And to find the epsilon, how do we find the epsilon? Probably something with the Hooke law, because we also have the Young modulus. Remember the formula for the, we have sigma equal E epsilon. So we have E, we can find epsilon, but we need to find also sigma. So for sigma, how do we find sigma? Sigma equal to force divided by the area. Looks good. We can find the area, we have the force, we have E, we can find epsilon, we can find epsilon, we can find the delta Y. So this is for the difference, the strain, the normal strain, the 8. So now for the other one with the gamma. Remember the gamma? The shear strain, that will be your delta x divided by, okay, I will talk about something there. Delta x divided by the h. And we have used a tangent of delta x divided by h. But when this delta x divided by h is very, very small, we can make the calculation, but the arctangent or just the delta x divided by h will be very, very close to. Very, very similar. There in our example, I think we need to go to 3 significative number to get a difference. Yes, at 3 significative numbers we have a difference, but it's very, very minimal. So it's less than 0.1%. So we can use gamma equal delta x divided by h. Okay, and how do we get the gamma? How would we get the gamma? We get the gamma with tau, the shearing stress equal the g time gamma. Yes. So same thing that the sigma equal E epsilon, the tau equal G time the gamma. And how do we find G? G, that's our like formula, the long formula, right? The epsilon divided by 2 time 1 plus the mu. And the mu is given. That's why we have the coefficient of Poisson in this example. Oh my God, I'm starting to get a bit everywhere and already very big. Okay, I will got it. That's fine. So I think we have the Poissons, we have the modulus, we can find the G. Okay, let's do one step at a time. Let's try to find number 1. Okay, let's find. Oh, we know we need the force. Oh, and I forgot just something. To tau. How do we find tau? We find tau with the shearing force divided by the area. So we need to find the shearing force. This is the formula that is missing. Okay. Keep all those formula close to you on the paper and see which one you can use and in which order to get from what is given to the final answers, the final questions. Okay, so we want to find sigma equal the force divided by A. Let's look at this little diagram there. We need to find the normal force and the friction force and the shearing force. So we have the 1.5, and this is at an angle 60 degrees. So those two forces are divided into a normal force and a shearing force. This normal force will be 1.5 sine 60 degree, and this shearing force on the top will be 1.5 cosine 60 degrees. Okay, so and we have our little pad on the bottom there. Little pad there. Oops. Let me, yeah, make it. I need to make that a little bit bigger because I keep changing the dimension. But here we go, like this. So we will have the same forces on this side and on this side, right? The same N and the same V. So sigma, we see that the normal force is 1.5 sine 60. So sigma equal 1.5 sine 60, and the area, that will be the top area there. So that will be divided by 100 times 75. So sigma, the normal, well, did I get that information? Normal stress. I don't know if I found it. Oh, here we go. Let me put it there again. So the sigma P normal divided by the 100 times 75. Oops, 0.173. Yes, I added 173 MPa. So we have sigma. We can find epsilon. Epsilon equals sigma divided by E. So epsilon equals 0.173 divided by the 5 megapascal. Epsilon equal by epsilon. Okay, let me just make sure I didn't make a mistake. Yes. Yes. So this is 0.0. I keep pushing on that. Okay, I need to find. Tell me if you know the way. Don't click on that on the bottom. Sometimes it disappears, sometimes it's come back. 4.6 millimeter. Okay, so we can find the delta y because we know that epsilon equals the delta y divided by h. So the delta y equals 0.0346 times the original h was 25. So the delta y equal, the delta y is very small, 0.87 millimeter. So the new h, the h final, will be 25 minus 0.87 millimeter. So h final equal 24.13 millimeter. Okay, this is for the normal strain and the change in dimension in the y directions. Now if we look at the gamma, the shearing, we have tau equal the shearing divided by the area, and we look at the area that is parallel to the shearing. So we have tau equal, the shearing force is 1.5 cosine 60 degrees, and the area that the same that the one on the top. This is the 75 divided by time 100. So the tau, that are the shearing stress, equal to 0.1. Oh, let me provide a little bit more. Oh, that's exactly 0.100 MPa. Okay, so we have the tau. Oh, we need to find G to find gamma. We need to find G. So G equal E divided by 2 times 1 plus mu equal, the E is provided is 5. 2 times 1 plus the Poisson ratio 0.45. That's a rubber, so it's kind of high. So G equal G 1.724 MPa. We are almost there. So now we can use the formula tau equal G times gamma, and we find gamma equal tau divided by G, so equal 0.100 divided by 1.724, gamma equal 0.0581. Is it this one? I just want to make sure. I don't think that this one. Let me do it. Equal 0.100 divided by 1.724. Yes, that this one, 0.0058. Okay. And let's say we can have two steps there, but oops. Let's say that gamma equal delta x divided by h, because we want to find delta x. This is about to be a tangent of delta x divided by h. You can make the calculation with the tangents, but let's do it without the tangents. You will see that's give us almost the same thing. So we have delta x equal gamma times h. So delta x equal gamma 0.058, that angle, and h, this is this h there, that is a 25. Delta x equal 1.45 millimeter. So that means that the rubber at the end looks like this. Okay, this is exaggerated, it's not that much, but the 8 at the end is 24.1, and this little distance there is 1.45 millimeter. Remember that this one is 100 millimeter, so it moves like of 1.5%. And in the other directions of the pad will not change because we don't apply forces in the other direction. No, what did I say? Probably that will be larger. That will be larger because of the normal force, but that's not what we are trying to find. Okay. Oops, this is this one. This is this one. So this is the new dimension of the pad. Okay. So that's the step that we did. I will say, make sure that you have all the formula available and see what you have and what you want. So in our case, we have some information of forces. So we have some forces, some area. We have also the module Young, the Poisson ratio that was provided. We were able to find easily the shear force and this area. So we're starting from those formula and up to the delta x, the strain in both directions, shearing strain and stress, and shear strength and normal strain. And we ended up finding this little difference of dimensions for the height and for the angle due to the shearing. Hope that makes sense. Bye bye.